Hey guys, welcome to this news story. Today, we set our sights on Saturn, the planet famous for its endless rings that circle it like frozen jewelry. From a distance, they shine with bright bands of ice and rock, stretching across hundreds of thousands of kilometers. But up close, the rings are alive with motion. Pieces collide, spin, and swirl, forming patterns that change constantly. Some areas are thick and bright, others almost empty, and every part moves at incredible speeds around the planet. What really lies beneath these dazzling layers? How have they stayed in place for so long while facing constant forces that try to tear them apart? Hidden interactions pull, push, and shape the countless particles, creating structures we're only beginning to understand. In this video, we dive into Saturn's rings to uncover their hidden secrets and explore what they teach us about the power and complexity of giant worlds. Saturn is the sixth planet from the Sun and the second largest in the solar system. Its size surpasses every other planet except Jupiter. The diameter of Saturn is about 120,536 kilometers, nearly 10 times that of Earth. Despite this size, Saturn has a very low density. In fact, its average density is less than water, which would allow the planet to float if placed in a large enough body of water. This low density comes from its composition, which is mostly hydrogen and helium, with small amounts of methane, ammonia, water vapor, and other trace gases. The mass of Saturn is about 5.68 times 10 to the power of 26 kilograms, more than 95 times that of Earth, yet its volume is so large that its surface gravity is only slightly stronger than Earth's. Its gravity shapes the environment around it and influences the behavior of particles, moons, and the rings that encircle the planet. Saturn's orbit around the Sun takes nearly 29.5 Earth years to complete. It moves in a nearly circular path at an average distance of about 1.43 billion kilometers. The planet rotates very quickly on its axis, completing a full rotation in just over 10 and a half hours. This rapid rotation causes the planet to flatten slightly at the poles and bulge at the equator. The atmosphere is layered, with the upper layers composed primarily of hydrogen and helium. Deeper layers increase in density and pressure, eventually blending into a thick, liquid metallic hydrogen region surrounding a small rocky core. These layers are important because they set the stage for the planet's magnetic field and the interactions that occur within its rings. The ring system of Saturn is the most extensive and complex in the solar system. Observed even with small telescopes from Earth, the rings appear as thin bands of light encircling the planet. Their total diameter extends more than twice the distance from Saturn to its largest moon, Titan, yet the rings themselves are extremely thin in comparison. The thickness of the main rings is often no more than 10 meters in many areas, making them nearly invisible from a side view. This dramatic ratio of width to thickness creates the striking appearance of flat, wide, and almost two-dimensional structures that hover above the planet. These rings are divided into several distinct regions. The most prominent are the A ring, B ring, and C ring. The B ring is the brightest and densest, containing a large concentration of particles. Between the A and B rings lies the Cassini division, a gap of several thousand kilometers in width. The A ring ends at the Encke gap, a narrower division formed by the gravitational influence of small moons. Beyond the main rings, there are fainter and more diffuse rings, sometimes referred to as the D, E, F, and G rings. Each of these has unique properties, particle sizes, and densities. The E ring, for example, is extremely wide but very faint, composed mainly of tiny ice particles originating from the Moon Enceladus. The particles that make up the rings vary in size from microscopic grains to chunks several meters across. Most are icy, reflecting sunlight and giving the rings their bright appearance. Some contain darker material, which may be rocky fragments or coated ice altered by radiation. Despite the appearance of solidity when viewed from a distance, the rings are made of countless independent particles. Each particle orbits Saturn independently, following the laws of orbital mechanics, yet collectively they form coherent patterns that can be observed as continuous bands. The rings are not uniform. There are regions where particles are densely packed, creating brighter areas, and regions where particles are sparse, resulting in darker bands. Waves ripple through the rings in the form of spiral density waves and bending waves. These waves arise from the gravitational influence of Saturn's moons and resonances within the ring system itself. They move slowly outward or inward, reshaping the local distribution of material over time. These patterns provide clues about the mass and structure of the rings, allowing scientists to calculate the total mass and understand the processes at work. Saturn has a strong magnetic field generated by motions in its metallic hydrogen interior. This magnetic field interacts with charged particles within the rings, creating small electric currents and influencing particle motion. The field traps plasma and energetic particles, forming a complex environment that extends beyond the visible rings. The interactions between the magnetic fields, charged particles, and ring material create faint halos and diffuse structures, which are detected by spacecraft instruments but are not visible in ordinary light. Observation of Saturn and its rings has evolved over centuries. Early astronomers using simple telescopes noted the presence of strange appendages around the planet. Galileo first saw them in 1610 but could not identify their true nature. Later, Christian Huygens correctly interpreted them as a flat ring surrounding the planet in 1655. Subsequent improvements in telescopes revealed divisions and structure within the rings. The Voyager missions in the late 20th century provided detailed imaging, while the Cassini mission, which orbited Saturn for over 13 years, delivered high-resolution data on particle composition, ring structure, and the interactions between rings and moons. The rings of Saturn exist within a balance of forces. Saturn's gravity pulls particles inward, while centrifugal forces from orbital motion push them outward. Collisions among particles spread material along orbital paths, but also keep it confined to narrow planes. The delicate equilibrium maintains the rings in their thin, flat state. Particles collide gently, often rebounding or sticking together temporarily, forming transient clumps. This dynamic behavior occurs continuously across billions of individual particles, shaping the structure of each ring region and creating features that can persist for years or even decades. Saturn's rings reflect sunlight with varying intensity depending on composition and density. The brightest regions correspond to areas where water ice dominates, while darker regions contain more dust or irradiated material. The ring's reflectivity changes slightly with viewing angle and solar incidence, providing information about particle orientation and surface roughness. By studying light reflected from the rings across different wavelengths, scientists can determine chemical composition, particle size distribution, and thermal properties. Seasonal variations affect the appearance of the rings. As Saturn orbits the Sun, the tilt of its axis changes the angle at which sunlight strikes the rings. Every 15 Earth years, Saturn reaches an equinox when the Sun passes directly over the ring plane. During this time, shadows cast by ring particles and embedded moons can be observed, revealing vertical structures and variations in particle density. Outside equinox, the Sun illuminates the rings from an angle, enhancing brightness contrasts and highlighting subtle wave patterns. The interactions of the rings with Saturn's moons further shape their structure. Small moons embedded within or near the rings act as shepherds, confining particles to narrow paths. Resonances with larger moons create gaps and waves, and periodic gravitational tugs cause oscillations in particle orbits. These interactions maintain the intricate structure seen in high-resolution images and ensure the rings are not evenly spread or diffused. Over long timescales, These processes continue to sculpt the rings, forming both permanent and transient features. Beneath the visible surface of the rings lies additional complexity. Fainter dust, tiny ice grains, and plasma contribute to a diffuse component that extends beyond the main ring plane. Observations in ultraviolet, infrared, and radio wavelengths reveal these components, which are not detectable in visible light. This extended material forms halos and tenuous clouds around the rings, interacting with Saturn's magnetosphere and contributing to the overall ring environment. Saturn's ring system provides insight into processes that occur in other planetary disks, including protoplanetary disks around young stars. The dynamics of particle collisions, wave formation, and resonances in Saturn's rings offer it a natural laboratory for studying how matter interacts under gravity, rotation, and collisions. Each observation of ring structure, particle composition, or wave behavior adds to understanding the evolution of planetary systems and the physical principles governing disk like formations. The scale of Saturn's rings is remarkable. While spanning hundreds of thousands of kilometers, their thickness is measured in meters. The ring's radial extent can reach up to 282,000 kilometers from the planet's center. Within this vast expanse, individual particles orbit at speeds between 8 and 32 kilometers per second, depending on their distance from Saturn. The combination of size, particle velocity, and particle density creates a dynamic system in constant motion. Scientific study of Saturn's rings continues to refine knowledge of their composition and structure. Cassini's final observations capture detailed images of ring edges, vertical warps, and fine structures. Analysis of particle mass, size distribution, and movement allows estimation of the total ring mass, which is comparable to the mass of a small moon. Thermal measurements determine temperature variations across different regions, revealing heating from solar radiation and internal energy from particle collisions. The rings are not permanent features. Observations suggest that material slowly spirals inward, gradually falling into Saturn due to drag forces and gravitational perturbations. Micrometeorite impacts erode particles and produce dust, which is either recycled within the rings or lost to space. Models of ring evolution indicate that while the rings may have existed for hundreds of millions of years, their current structure may be relatively young in planetary terms. Despite ongoing changes, the rings remain a defining feature of Saturn, reflecting the balance of forces and processes that govern planetary ring systems throughout the solar system. The rings of Saturn are made up of billions of small particles that orbit the planet in thin, flat layers. These particles range in size from tiny grains, smaller than a millimeter, to chunks as large as several meters across. Most of the material consists of water ice, which reflects sunlight strongly and gives the rings their bright appearance. Mixed with ice are darker particles made of rock or dust. Some of this darker material may have originated from small moons that broke apart or from meteoroids that collided with the rings. The combination of ice and rock produces variations in brightness and color across the rings, creating patterns that can be observed from spacecraft and telescopes. The main rings are divided into several regions, each with unique characteristics. The B ring is the most massive and dense, containing the largest concentration of particles. Its surface appears brighter than other rings due to the high content of ice. The A ring is slightly less dense and is separated from the B ring by the Cassini division, a wide gap spanning thousands of kilometers. The C ring lies inward of the B ring and is more transparent, containing fewer particles and more fine dust. Fainter rings, such as the D, E, F, and G rings, lie either closer to the planet or extend farther outward. The E ring, in particular, is very wide but diffuse, composed mainly of tiny ice particles ejected from the moon Enceladus through its geysers. Within these rings, the particles are not evenly spread. Some areas are densely packed, forming bright bands, while others are sparse, resulting in darker gaps. These density variations are influenced by the gravitational forces of Saturn and its moons. Collisions among particles also play a role, breaking larger chunks into smaller pieces or causing small clumps to form temporarily. Despite the movement and collisions, the overall ring structure remains stable due to the balance between Saturn's gravity and the centrifugal force of orbiting particles. Each particle moves independently, yet their collective behavior produces the visible bands that encircle the planet. The Cassini division is one of the most prominent gaps in the rings. Located between the A and B rings, it spans roughly 4,800 kilometers. The gap is not empty. It contains some particles, but they are much less dense than in the surrounding rings. The division exists because of orbital resonances with Saturn's moon Mimas. Particles in this region experience regular gravitational tugs from Mimas, which prevent them from remaining in stable orbits and keep the area relatively clear. Smaller gaps, such as the Encke gap within the A ring, are maintained by tiny moons, often called shepherd moons. These moons move within or near the rings, pulling particles toward or away from their orbits and helping to preserve narrow gaps and sharp ring edges. The particle composition of Saturn's rings is primarily water ice, which can range from nearly pure ice to mixtures with rock and dust. Spectroscopic analysis shows that ice particles can be coated with thin layers of other materials, altering their reflectivity and color. In some regions, ice appears very bright, reflecting most sunlight. In darker regions, ice is mixed with more rocky material or covered by fine dust from meteoroid impacts. These surface variations are essential for understanding the origin and evolution of the rings, as they indicate processes of erosion, coating, and renewal that occur over time. Particle sizes affect how the rings appear in different observations. Small grains scatter light differently from larger chunks, creating variations in brightness and color. Fine dust is influenced more strongly by electromagnetic forces in Saturn's magnetosphere, while larger particles follow nearly perfect orbital paths determined by gravity. In addition, collisions among particles generate waves and ripples. These patterns can be measured, showing the density and spacing of particles in each ring region. The largest particles move more slowly in collisions, while smaller grains are more easily scattered or carried along by transient forces. The structure of the rings is layered and complex. Bright and dense bands alternate with darker, less dense zones. Vertical structure is minimal. Most particles remain within a thin plane. However, small vertical warps exist, often caused by interactions with moons or local gravitational instabilities. These warps are typically a few tens of meters in height, small compared to the ring width. They are visible only in detailed spacecraft images, showing that the rings are not perfectly flat but have subtle undulations. Even these minor variations contribute to the overall dynamics, as particles move up and down slightly while orbiting Saturn. Shepherd moons influence the rings on multiple scales. Their gravity confines particles to narrow paths, keeping the edges of rings sharp and maintaining gaps. They also create wave patterns in nearby particles. For example, small moons embedded in the F ring produce braided structures, loops, and clumps. These features change slowly over time as the moons move along their orbits. The moons act as regulators, keeping the particles from spreading too widely, while allowing interactions that create patterns and structures. Their presence demonstrates the balance between gravitational forces and particle motion in maintaining the ring system. Within the rings, collisions among particles occur frequently. Most collisions are gentle, as the relative velocities of particles are generally low, ranging from a few millimeters to meters per second. When collisions happen, particles may bounce off one another, break into smaller fragments, or stick temporarily to form clumps. Over time, these interactions redistribute material, smoothing out irregularities and maintaining the overall structure. In some cases, repeated collisions create spiral density waves, which propagate through the rings and reveal the underlying gravitational influences of moons and Saturn itself. The ring gaps are not uniform or empty, but contain fine particles that respond differently to forces. Dust and small ice grains can move into gaps temporarily, creating faint structures detectable in high resolution images. These particles are affected by gravitational tugs from moons, radiation pressure from the sun, and charged particle interactions within Saturn's magnetosphere. As a result, gaps appear dark, but are not completely devoid of material. Observations show that even within the most prominent divisions, low density particle populations exist, contributing to subtle brightness variations across the rings. The rings are mostly composed of ice, but the presence of rocky material is significant. Rock may originate from shattered moons, comets, or meteoroids that collided with the ring system. These materials mix with ice, creating areas that reflect less light and appear darker. Analysis of reflected light across multiple wavelengths allows scientists to determine the proportion of ice to rock in each region. Bright icy bands indicate nearly pure water ice, while darker bands indicate higher concentrations of rock or irradiated particles. This distribution of materials provides clues about the formation history of the rings and the processes that continue to shape them. Temperature variations within the rings also influence their appearance and behavior. Ice particles closer to Saturn or exposed to direct sunlight reach higher temperatures than particles in shadowed regions. Thermal differences affect how particles collide and stick together, influencing clumping and fragmentation. Fine dust heats up quickly but cools down rapidly, while larger chunks retain heat longer. Temperature measurements help scientists understand the energy balance within the rings and the physical properties of particles, such as density, porosity, and surface roughness. The outer rings, such as the F and G rings, are narrower and more tenuous than the main A and B rings. They are composed primarily of small ice grains, often with irregular distribution. These rings are maintained by the gravitational influence of nearby moons and resonances with larger moons further out. The F ring, in particular, shows complex braids and clumps caused by interactions with shepherd moons, Prometheus and Pandora. These narrow rings demonstrate the sensitivity of ring particles to gravitational forces and the fine balance required to maintain their structure over long periods. Dust and small ice grains within the rings interact with Saturn's magnetic field. Charged particles follow magnetic field lines, creating faint halos around the main rings. The plasma environment contributes to slow erosion of ice particles, adding fine material to the diffuse ring components. Even though these effects are subtle, they play a role in shaping the long-term evolution of ring density and composition. The interaction between electromagnetic forces and particle motion demonstrates that ring dynamics are influenced by multiple forces simultaneously, not only gravity. Observations by spacecraft, especially Cassini, have revealed detailed structures within the rings. Imaging shows thousands of narrow gaps and density waves and subtle brightness variations. These features provide a map of particle distribution, sizes, and interactions. Cassini also measured mass and thickness of the rings in specific regions, confirming that the densest areas are concentrated in the B ring. The data suggest that while the rings are massive in appearance, the total mass is comparable to a small moon, distributed over an area hundreds of thousands of kilometers across. The ring's composition and structure are closely linked to ongoing processes. Collisions, gravitational interactions, and exposure to radiation continually modify particles. Some regions show evidence of particle aggregation, while others indicate erosion and fragmentation. Fine dust settles slowly toward the ring plane, replenishing areas of low density. These processes occur over timescales ranging from hours to millions of years. Observations of changes in ring structure over time provide insight into the dynamic nature of the system and the forces maintaining its stability. Bright, icy regions and darker bands together reveal a history of collisions, erosion, and interaction with moons. Variations in particle size and composition contribute to ring reflectivity and observed structure. The rings are not uniform sheets, but collections of countless individual particles, each following physical laws while responding to local forces. The combination of particle composition, size distribution, density variations, and gravitational interactions produces the patterns observed today, which continue to evolve slowly yet maintain recognizable structures across the vast ring system. The diversity of particle sizes ensures complex behavior. Small grains respond quickly to collisions and forces, while larger chunks move more steadily along their orbits. Some particles are coated with fine dust from impacts, while others remain pure ice. The mixture of materials creates contrast across the rings. High resolution imaging shows that even small variations in density can produce noticeable changes in brightness, revealing the intricate organization of particles, the structure of gaps, divisions, and wave. Patterns reflects both current interactions and long-term processes that have shaped the rings over millions of years. The A and B rings remain the most studied regions due to their density and visibility. Brightness variations correspond to both composition and particle spacing. Spiral waves propagate through these rings, resulting from gravitational resonances with moons. The Cassini division and Encke gap remain key areas of interest because they demonstrate how moons can clear paths in a dense particle field. The detailed structures within these regions highlight the dynamic yet stable nature of Saturn's ring system, where interactions at small scales affect the appearance of the rings across thousands of kilometers. Even faint rings, like the E and G rings, contribute to understanding the overall structure. These low-density regions show how particle size and composition vary with distance from Saturn. Tiny ice grains dominate, often replenished by active moons such as Enceladus. The diffuse material extends over great distances, illustrating that the ring system is not confined to the bright visible bands, but includes broader components that interact with Saturn's gravity, magnetic field, and the motions of nearby moons. The interplay of material composition, particle size, and density produces the visual complexity of the rings. Bright icy bands indicate dense, reflective material, while dark regions suggest mixtures of rock, dust, and irradiated ice. Variations in size and mass of particles create differential motion, influencing local collisions and clumping. These processes are continuous, producing subtle changes while maintaining the overall appearance of ordered rings. The structure seen today results from a balance of forces, ongoing interactions, and the combined effects of millions of independent particles forming a coherent system. The particles in Saturn's rings follow precise paths dictated by the planet's gravity. Each particle orbits Saturn in its own trajectory, moving in a nearly circular path. The closer a particle is to the planet, the faster it travels. Those further away move more slowly. This relationship follows the principles of orbital mechanics, often described by Kepler's laws. The speed of each particle depends on the distance from Saturn, creating a gradient in velocity across the rings. Particles near the inner edge of a ring travel at tens of kilometers per second, while those near the outer edge move more slowly. Despite the large number of particles, each moves independently while interacting with neighbors. Collisions occur frequently, but are generally gentle because the relative velocities between nearby particles are low. When collisions happen, particles may bounce off each other, break into smaller fragments, or temporarily stick together, forming clumps. These interactions are essential for redistributing material and shaping local structure. Over time, repeated collisions smooth out irregularities, creating stable patterns within the rings. Orbital resonances play a significant role in shaping motion within the rings. When a particle completes a certain number of orbits in the same time that a moon completes its orbit, repeated gravitational tugs influence the particle's path. These resonances can cause particles to cluster, creating waves or clearing regions that become gaps. Spiral density waves arise from these interactions. They appear as tightly wound, spiral like ripples in the ring, caused by periodic gravitational forces. The waves travel through the ring material, moving slowly outward or inward, depending on the location and the resonance. Self gravity also affects ring dynamics. Groups of particles exert gravitational pull on one another, creating small clumps that can persist temporarily. These clumps, sometimes called self gravity wakes, are elongated structures that align with the direction of orbital motion. Although individual particles remain separate, their combined gravitational influence produces observable patterns. These wakes are visible in high resolution imaging, showing variations in brightness and density that shift over time. The combination of collisions and self gravity results in complex local behavior. Some regions show high particle density with frequent interactions, while others are more diffuse. Collisions fragment larger chunks into smaller pieces, while self gravity pulls particles together into temporary clumps. This constant interplay of forces maintains the thin, flat structure of the rings while producing visible patterns. The system remains in dynamic equilibrium, balancing the energy of motion with the organizing effects of gravity. Particles do not orbit in perfect planes. Small vertical motions occur as particles respond to nearby masses and collisions. These vertical displacements are typically only a few meters, small compared to the radial width of the rings. Even minor vertical movements influence local particle density, affecting the appearance of waves and clumps. Observations from spacecraft show that these subtle vertical variations produce shadowing effects and brightness differences in images taken from different angles. The velocity gradient across the rings creates shear. Inner particles move faster than those just outside, causing a slow stretching of local clumps along the direction of motion. This shear contributes to the formation of spiral density waves. As gravitational resonances pull on particles, the waves propagate through the ring, often interacting with other features to create overlapping patterns. These interactions are visible as faint ripples and bright streaks in detailed imaging. Collisions between particles are a central aspect of ring dynamics. Most collisions are low energy, with particles bouncing or sliding past each other. Larger chunks may break apart, generating additional smaller particles. Over long periods, collisions continually modify the size distribution, eroding some particles while building transient aggregates. These processes explain the wide range of particle sizes observed, from micrometer grains to meter scale chunks. Collisions also dissipate energy, preventing particles from moving chaotically and helping maintain the thin, flat structure of the rings. The distribution of particle sizes contributes to the behavior of density waves. Small grains respond more readily to pressure from surrounding particles and to subtle forces such as radiation or plasma drag. Larger particles follow orbital paths more consistently but contribute significantly to local gravity, influencing the motion of nearby smaller particles. This mixture of sizes and masses creates regions of higher and lower density, which form the bright and dark bands observed across the rings. Self-gravity wakes are elongated clusters of particles formed by local gravitational attraction. These wakes are typically aligned along the direction of orbital motion and extend for hundreds of meters. Individual particles within a wake remain separate, yet their combined gravity affects the motion of neighbors. Wakes produce small-scale structure and brightness variations, contributing to the intricate appearance of the rings. The formation and dissolution of these wakes occur continuously as collisions break clumps apart and gravity reforms them elsewhere. Spiral density waves propagate through the rings at a predictable speed determined by local particle density and Saturn's gravitational influence. They originate where gravitational resonances with moons create repeated perturbations. The waves compress particles in certain regions and stretch them in others, creating alternating bands of higher and lower density. Over time, these waves maintain coherence, moving across thousands of kilometers of ring material. Observations of these waves provide data on particle mass, density, and the overall structure of the rings. The interplay between collisions and orbital motion creates a system that is dynamic yet stable. Collisions redistribute particles, while orbital motion keeps them in their respective rings. Resonances with moons shape large scale patterns, and self gravity forms temporary clumps. Each particle responds to multiple forces simultaneously, producing complex but predictable behavior. The balance between these forces maintains the rings over long periods while allowing small, continuous evolution. Even within narrow gaps, particles are in motion. Sparse material may drift in and out of gaps, influenced by nearby resonances or shepherd moons. Tiny ice grains may scatter into gaps, while larger particles remain confined to dense regions. Observations show that gaps are not completely empty, but contain low density populations, which respond dynamically to local forces. These sparse particles contribute to faint features, such as arcs or halos, revealing ongoing motion and interaction, even in areas with few large chunks. The ring's dynamics are influenced by Saturn's gravity, the gravitational pull of moons, particle collisions, and self gravity. These combined forces produce patterns at multiple scales, from small wakes to large spiral waves. Each component of the system interacts continuously, shaping particle motion and distribution. The result is a complex, ever changing, but coherent structure that persists over time, with motion and energy balanced across billions of individual particles. Velocity gradients cause shearing effects within dense ring regions. Faster moving inner particles stretch clumps along the orbit, while slower outer particles follow more widely spaced paths. This shearing influences the formation of waves and wakes, redistributing material across the ring plane. Over time, these effects produce long, narrow streaks of higher or lower density, visible in detailed imaging as lines, ripples, and undulations. The constant movement of particles results in collisions that are both disruptive and constructive. When particles collide at low speeds, they may stick together temporarily, forming clumps that last for minutes, hours, or longer. High speed impacts can fragment larger pieces, producing smaller particles that disperse through nearby regions. These processes maintain a wide range of particle sizes and help regulate the density and brightness of the rings. Spiral density waves interact with self gravity wakes, creating complex overlapping patterns. As waves move through dense regions, they compress material while wakes form in the compressed zones. The interaction between these structures produces subtle brightness variations, detected in both visible and infrared observations. These features change slowly over time, reflecting the dynamic equilibrium maintained by collisions, gravity, and orbital motion. Collisions also generate fine dust, which interacts with the plasma environment. Small particles are more easily influenced by electromagnetic forces, while larger chunks are primarily affected by gravity. This distribution of forces contributes to subtle changes in particle orbits, especially in low-density regions. Over long periods, such processes help shape the overall evolution of the rings, influencing density gradients, particle composition, and the appearance of faint gaps and arcs. The ring's particle motion is remarkably ordered despite the large number of particles. Each particle follows predictable paths determined by Saturn's gravity, while interacting with neighbors through collisions and gravitational pulls. The resulting dynamics produce coherent structures such as waves, wakes, and clumps, which are visible across the radial and azimuthal extent of the rings. This order emerges from the combination of simple physical laws applied to an immense number of small bodies, creating a system of extraordinary complexity and stability. Vertical motion within the rings is limited, yet it plays a role in dynamics. Small deviations from the ring plane allow particles to oscillate slightly above or below the main plane. These motions interact with spiral waves and wakes, producing minor fluctuations in density and brightness. Spacecraft observations confirm these effects, showing small shadows and brightness differences that reveal vertical undulations of a few meters. Even these minor vertical displacements influence local collisions and particle organization. The combined effects of orbital motion, collisions, self gravity, and resonances produce a system in constant motion but in equilibrium. Inner particles orbit faster, shearing material. Collisions redistribute energies and mass. Self gravity forms temporary clumps. Resonances with moons shape large scale patterns. Together, these processes maintain the thin, flat structure of the rings, while generating the complex and detailed patterns observed in high resolution images. Saturn is orbited by dozens of moons, ranging in size from small moonlets just a few kilometers across to large bodies hundreds of kilometers in diameter. Some of these moons orbit close to the planet, moving among or near the rings, while others remain at greater distances. Each moon exerts a gravitational pull on surrounding material, and even small moons can influence the structure and motion of the rings. Their presence introduces forces that shape gaps, create waves, and regulate the distribution of particles over long distances. Major moons such as Mimas, Enceladus, Tethys, Dione, Rhea, and Titan orbit beyond the main rings, but still affect the ring system. Their gravitational fields produce resonances, regions where the orbital period of ring particles is a simple fraction of the moon's orbital period. These resonances create repeating gravitational tugs that alter particle orbits. Over time, such interactions can clear paths in the rings, forming gaps or compress particles into higher density bands. These effects are particularly noticeable in the A ring and in areas adjacent to the Cassini division. Within and near the rings, smaller moons, often referred to as shepherd moons, play a crucial role in maintaining sharp ring edges and narrow gaps. Prometheus and Pandora, for example, orbit near the F ring and confine its material. Prometheus moves just inside the ring, pulling particles inward, while Pandora moves outside, pulling them outward. This combined gravitational influence prevents the ring material from spreading and maintains the thin, narrow structure observed in high resolution images. The continuous tug of war between these moons and the ring particles produces loops, kinks, and clumps, visible as changing features along the ring over time. Shepherd moons not only confine ring edges, but also produce waves in the surrounding material. As a moon passes near a section of the ring, its gravity temporarily accelerates nearby particles, creating ripples that propagate through the ring plane. These waves can appear as bright and dark streaks, which are measured in observations to understand particle density, orbital speed, and local interactions. The gravitational influence of moons ensures that these waves remain regular and persistent, rather than dispersing quickly across the ring system. Tiny moonlets embedded within the rings also contribute to structure. These small bodies, only a few kilometers across, carve narrow channels or arcs in the ring material. Particles near these moons may temporarily orbit in clustered formations, forming transient clumps or wakes that trail the moon's path. As the moon moves, the clumps disperse and reform, creating patterns that are visible only in detailed imaging or by measuring brightness variations. Even these small moons, though insignificant in mass compared to Saturn, influence local particle motion over extended periods. Resonances between moons and ring particles are a major driver of ring gaps and waves. When a particle orbits Saturn in such a way that it completes an exact fraction of a moon's orbit in the same time the moon completes one orbit, repeated gravitational tugs accumulate. Over thousands or millions of orbits, these periodic forces displace particles, producing low-density regions or creating sharp edges. The Cassini division, for example, corresponds to a resonance with the moon mimas, which exerts repeated pulls that prevent particles from remaining in stable orbits within that region. Other resonances create spiral density waves that propagate through the rings. These waves appear as tightly wound patterns of compressed and stretched particles. In some regions, multiple waves overlap, producing interference patterns that enhance or reduce local density. By studying these waves, scientists can determine particle mass, distribution, and the strength of gravitational interactions. Each wave is a record of past and present forces acting on the ring particles, showing how moons continually shape ring structure. Some moons orbit between or near gaps within the rings. Pan, for instance, resides within the Encke gap in the A ring. Its gravity clears material from its immediate orbit, maintaining the gap while simultaneously creating edge waves along the ring boundaries. The motion of Pan perturbs nearby particles, which move slightly inward or outward, generating small ripples along the gap edges. Such interactions are repeated each orbit, reinforcing the structure of the gap and maintaining the clear separation between adjacent dense regions. Even distant moons influence the rings indirectly. Larger moons, though orbiting farther away, exert gravitational forces that create resonances over extended regions. These forces can compress or stretch particles across thousands of kilometers, forming alternating bands of density or brightness. Over long timescales, the cumulative effect of these interactions shapes the large-scale structure of the ring system, ensuring that rings do not disperse and that density variations remain coherent. The relationship between moons and rings is not one-sided. The rings also affect moon orbits slightly by exchanging angular momentum. Collisions with ring particles, though minor for large moons, contribute to small orbital adjustments over millions of years. In some cases, the accumulation of material in specific areas can modify the gravitational environment, influencing the behavior of moons nearby. This mutual interaction illustrates the dynamic nature of Saturn's system, where even relatively small bodies participate in continuous exchanges of energy and momentum. Shepherd moons often produce visible clumps, kinks, and streamers within rings. As they pass near dense regions, their gravitational influence creates temporary features that persist for hours or days. Prometheus, moving along the inner edge of the F ring, can pull strands of material away from the main ring, forming elongated structures that drift before settling back into place. These events show that even small moons play an active role in shaping the ring's appearance at both large and small scales. Particles within resonance zones experience gradual shifts in orbit. Repeated gravitational tugs cause some particles to move outward while others shift inward. Over time, these shifts create clear gaps or reinforce density waves. The orbital period of a particle relative to a moon determines the location and strength of these features. High-density regions often correspond to stable zones, while low-density regions mark areas where resonances prevent long-term stability. Mapping these patterns allows scientists to predict moon locations and understand gravitational influences across the rings. Moon-driven structures also appear in faint, narrow rings. Small moons embedded within the G and E rings influence local particle distribution. Even with low particle density, the gravitational effects of these bodies produce arcs, strands, and narrow bands. Observations show that these faint rings are not featureless. Instead, they respond dynamically to the presence of moons, demonstrating that gravitational interactions are active throughout the entire ring system, regardless of density. The gravitational influence of moons extends vertically as well as radially. As a shepherd moon passes near a ring, its pull can lift particles slightly above or below the main plane, creating small warps. These vertical disturbances are generally minor, measured in tens of meters, yet they contribute to the overall three-dimensional structure of the rings. Shadowing effects and imaging from multiple angles reveal these subtle undulations, showing that moon interactions affect not only the horizontal distribution of particles but also their vertical arrangement. Some moons, while distant, act as long term sculptors of the rings. By maintaining resonances over thousands of orbits, they keep gaps open and prevent particle accumulation. Other moons, moving closer to the rings, produce temporary but repeated disturbances. These disturbances generate complex patterns, including braids, kinks, and waves that appear and disappear as the moons continue their orbital paths. The combination of stable and transient effects creates a layered and evolving structure across the ring system. The F ring, with its narrow width and dynamic features, exemplifies the influence of moons. Prometheus and Pandora interact continuously with the ring particles, creating loops, strands, and clumps. As Prometheus approaches, it pulls material away from the main ring, forming elongated structures. Pandora's gravitational pull on the outer edge restrains the material, preventing excessive spreading. This interaction is cyclical, producing ongoing changes visible in images and measurements. Such dynamics demonstrate how moon ring interactions sustain sharp edges and localize complexity within narrow rings. Gaps, like the Encke gap and Keeler gap, illustrate the effect of embedded moons. Pan resides in the Encke gap, while Daphnis occupies the Keeler gap. Each moon clears particles along its orbit while inducing edge waves and ripples in nearby material. These waves propagate through the rings, producing bright and dark streaks that reveal local particle density and orbital response. The movement of these moons ensures that gaps remain stable, while continuous perturbations maintain the fine-scale structure observed today. Even smaller moons and moonlets, often less than a few kilometers across, influence their surroundings. These bodies create tiny arcs, clumps, or wakes as they move along their orbits. The particles nearby respond to repeated gravitational tugs, forming temporary structures. While these features may appear subtle compared to the major gaps, they are measurable in high resolution, imaging and contribute to understanding how small bodies regulate particle motion and ring structure. Resonances with moons also produce spiral waves in ring material. Particles in resonance experience periodic accelerations, generating ripples that extend radially through dense regions. These spiral density waves reveal the interaction of moons with ring particles across thousands of kilometers. The waves can overlap, creating interference patterns that highlight differences in local density and particle size. Observations of these waves allow scientists to infer the mass and distribution of particles as well as the locations and influence of resonant moons. The interaction between moons and rings occurs continuously. Particles respond to gravitational tugs, collisions redistribute material, and waves propagate throughout the system. Shepherd moons confine edges, embedded moons maintain gaps, and distant moons sustain resonances. This multi-scale system illustrates how Saturn's moons actively regulate and sculpt the rings, creating a dynamic yet stable environment that evolves over time while preserving the overall structure and complexity of the ring system. The origin of Saturn's rings has been a subject of study for many decades. Scientists consider multiple hypotheses to explain how the rings formed and how long they have existed. One leading idea suggests that the rings are primordial, forming at the same time as Saturn itself over 4 billion years ago. In this scenario, the rings consist of material left over from the planet's formation that never coalesced into a moon. Over time, collisions and gravitational forces shaped this material into the thin, extensive ring system observed today. An alternative hypothesis proposes that the rings are relatively young, perhaps only a few 100 million years old. According to this idea, the rings formed when a comet, asteroid, or small moon approached Saturn too closely and was broken apart by tidal forces. The debris from such an event would spread into orbit, forming the dense, icy rings. Evidence for recent formation includes the high reflectivity of the rings, which suggests that the particles are largely composed of clean ice. Over billions of years, meteoroid impacts would darken the ice if the rings were extremely old, but the bright appearance indicates ongoing renewal or a younger age. Observations from spacecraft have provided key evidence to examine these theories. The Voyager missions of the 1980s captured detailed images of ring structure and brightness. Voyager data revealed sharp edges, gaps, and density waves, which helped scientists estimate particle size, distribution, and composition. Later, the Cassini mission provided even more precise measurements, including mass, thickness, and detailed chemical composition. Cassini's instruments analyzed reflected light across multiple wavelengths, showing variations in ice purity, rock content, and dust distribution. These observations are critical for understanding both the origin and evolution of the rings. Ring erosion is an ongoing process influenced by multiple factors. Meteoroid impacts continuously strike the rings, chipping away ice and producing fine dust. Collisions among ring particles themselves also contribute to gradual fragmentation. Over time, these processes remove material from the rings, either by spreading dust outward or by drawing particles inward towards Saturn, where they eventually enter the planet's atmosphere. The slow loss of material suggests that if the rings were extremely old, they would be less massive and darker than what is observed today. Replenishment mechanisms are also important for maintaining the rings. Some material comes from Saturn's moons. Enceladus, for example, ejects icy particles through geysers at its south pole. These particles feed the E ring and may also contribute to nearby regions. Smaller collisions between moons or ring particles release additional debris, compensating for material lost through erosion. Over long periods, this continuous cycle of erosion and replenishment maintains the structure, density, and brightness of the rings. Particle loss occurs gradually across the ring system. Fine dust is particularly vulnerable to radiation pressure from the sun and electromagnetic forces within Saturn's magnetosphere. These particles can be slowly pushed outward or inward, eventually leaving the ring plane. Larger particles are more stable, but still experience slow erosion through repeated collisions and micrometeoroid impacts. The balance between particle loss and replenishment affects the overall mass of the rings, influencing estimates of their age and stability. Cassini data revealed detailed mass estimates for different rings. The densest regions, such as the B ring, contain the majority of the system's mass, while outer and diffuse rings like the E and G rings hold significantly less material. Mass distribution, combined with measurements of particle size and density, allows scientists to model erosion rates and predict how long the rings could persist. These models suggest that, without replenishment, the rings might gradually thin over hundreds of millions of years, supporting theories of both young and moderately aged rings. The composition of ring particles provides clues about formation. Pure ice dominates most of the visible rings, while darker regions contain more rock and dust. The high reflectivity of the A and B rings indicates that the ice is relatively clean, which is difficult to reconcile with a very old, primordial origin unless continuous renewal occurs. Conversely, the presence of darker material, especially in the C ring, suggests accumulation of meteoroid dust over long periods. These contrasts imply that the rings have experienced both erosion and replenishment, with material mixing and redistribution shaping the observed appearance. Gravitational interactions with moons also influence formation and evolution. Shepherd moons help maintain ring edges, preventing outward spreading, while resonances with distant moons shape gaps and density waves. Over time, these interactions can redistribute particles and influence erosion patterns. Some small moons embedded in rings may themselves be remnants of past disruptions, suggesting that collisions and breakups have occurred repeatedly throughout the system's history. Such events may contribute to the continuous cycle of particle loss and replenishment. Erosion and renewal processes operate at different scales. Micrometer sized dust is influenced primarily by collisions and electromagnetic forces, while meter scale chunks respond mostly to gravity and direct impacts. The combination of small and large scale processes ensures that the rings evolve gradually while preserving recognizable patterns. Collisions break large particles into smaller pieces, while self gravity and resonances cause local clumping and waves. These ongoing processes reveal that the rings are dynamic systems, continuously changing over both short and long timescales. Evidence from meteoroid bombardment provides additional insight. Impact craters on larger ring particles and moons indicate the frequency and size of collisions. Fine dust observed in the rings is often the result of such impacts, eroding ice and contributing to the faint, diffuse rings. Observations suggest that the rate of meteoroid bombardment has varied over time, affecting the rate of erosion and the appearance of the rings. This continuous process highlights that ring particles are not static, but are constantly undergoing physical changes. Thermal and radiative processes also influence particle erosion. Sunlight heats exposed surfaces of ice particles, leading to sublimation of the outer layers in some cases. Radiation interacts with surface ice, causing slow chemical changes that can darken the particles over long periods. The balance between exposure, sublimation, and replenishment determines how particle brightness evolves. Regions with higher replenishment rates, either from collisions or moon ejections, maintain brighter, cleaner ice, while less active areas gradually darken. The balance between formation, erosion, and replenishment allows for a wide range of possible ring ages. If the rings formed billions of years ago, continuous erosion must have been counteracted by replenishment from moons and collisions. If they formed more recently, their current mass and brightness could result from the disruption of a moon or comet. Both scenarios must account for the observed structure, particle size distribution, and chemical composition across the ring system. Analysis of these factors continues to refine estimates of ring age. Cassini observations of ring particle composition provide evidence of complex formation history. Ice purity varies across the rings, indicating differences in exposure and renewal rates. Darker material likely originates from both meteoroid impacts and incorporation of older, pre existing rocky debris. This mixture suggests that the rings have experienced multiple processes, including fragmentation of larger bodies, deposition of external dust, and internal collisions, each contributing to the present structure. Long-term evolution of the rings involves gradual changes in density, particle size, and structure. Spiral waves, self-gravity wakes, and edge structures remain stable over long timescales, but individual particles continuously collide, fragment, or aggregate. Some particles slowly spiral toward Saturn due to drag or perturbations, while others may migrate outward under specific forces. This slow evolution demonstrates that the rings are both resilient and fragile, maintaining coherent patterns while constantly exchanging material on a microscopic level. Models of particle dynamics, combined with observational data, suggest that the rings may persist for hundreds of millions of years, with some regions more stable than others. Dense inner rings retain material longer due to strong gravitational confinement, while outer diffuse rings are more easily dispersed. The interplay of formation processes, ongoing erosion, and replenishment mechanisms creates a dynamic balance, allowing the system to sustain its appearance over geological timescales. Particle aggregation contributes to the longevity of the rings. Small ice grains may stick together temporarily, forming clumps that survive multiple orbits. These clumps can grow gradually through collisions, while other processes break them apart. This constant cycle of formation and fragmentation ensures a range of particle sizes persists throughout the ring system. Observed density variations correspond to these cycles, illustrating the combination of disruption and aggregation shaping the rings over time. The formation and evolution of gaps and divisions are also linked to ring age. Resonances with moons create structured gaps, while local particle collisions and self gravity organize material into dense bands. The pattern and scale of these features provide clues about the history of gravitational interactions and particle redistribution. Detailed imaging of these structures allows scientists to model the long term evolution of the rings and estimate the timing and frequency of significant events, such as moon breakups or comet disruptions. Observations suggest that ring material may be recycled. Collisions and tidal interactions produce dust and ice fragments that slowly migrate through the system. Some particles are destroyed and reformed repeatedly, contributing to a cycle of renewal. This continuous turnover helps maintain the bright, reflective appearance of the rings while compensating for gradual erosion. The interplay between loss and renewal demonstrates that the rings are not static, but dynamically sustained over time. The brightness and sharpness of ring features are consistent with ongoing replenishment and relatively young ice surfaces. Even in the presence of continuous meteoroid impacts, the rings maintain high reflectivity due to particle turnover. Ice expelled from moons, like Enceladus, contributes additional material, maintaining local density and reflecting sunlight. This process highlights the combination of internal and external mechanisms that influence ring evolution and provide evidence supporting younger or moderately aged formation scenarios. Ring particles are composed primarily of water ice, with small amounts of rock and dust mixed in. Their surfaces are varied, ranging from smooth, reflective ice to rougher, darker patches where impurities or erosion have accumulated. Albedo, or reflectivity, is a key feature of these particles, determining how much sunlight is reflected versus absorbed. In the A and B rings, particles generally have high albedo, reflecting a large portion of incoming light. The C ring and other diffuse regions are darker, indicating a higher fraction of rocky material or accumulated dust. Variations in albedo create visible patterns across the rings, helping to distinguish dense bands from sparse areas and revealing subtle structural details in both bright and faint regions. Thermal behavior of ring particles is influenced by sunlight, Saturn's shadow, and the particle's own thermal properties. During exposure to sunlight, ice surfaces warm, reaching temperatures that vary depending on particle size, composition, and local ring density. Smaller particles heat and cool more quickly than larger chunks due to their higher surface area to mass ratio. When passing into Saturn's shadow, surfaces cool rapidly, sometimes by tens of degrees Kelvin. Seasonal changes also affect temperature, with the planet's tilt altering sunlight angles and intensity over years. These variations influence sublimation rates, which can slowly erode surfaces and contribute to redistribution of ice and dust. Micrometeorite impacts continually affect the surfaces of ring particles. Tiny meteoroids strike at high velocity, chipping away ice, creating small craters, and generating fine dust. Over time, repeated impacts darken surfaces by embedding dust and altering the ice's reflectivity. Crater sizes and frequency provide insight into the flux of micrometeoroids in the Saturn system. Smaller impacts dominate, gradually reshaping surfaces without destroying entire particles. Larger collisions are rare but contribute significantly to fragmentation and local debris clouds, supplying material that spreads through neighboring ring regions. Surface weathering from impacts and radiation slowly modifies the physical and chemical properties of particles. Ultraviolet radiation, charged particles from Saturn's magnetosphere, and repeated collisions alter ice chemistry, creating thin layers of altered material. This weathering can change spectral properties, slightly reducing reflectivity in some wavelengths while increasing scattering in others. High-resolution spectral measurements allows scientists to detect subtle changes in composition, differentiating fresh ice from weathered surfaces, and providing information about ongoing surface evolution. Porosity is an important characteristic of ring particles. Many particles are not solid blocks of ice, but rather aggregates of smaller grains with internal voids. This porosity affects thermal properties, mechanical strength, and how particles respond to collisions. Highly porous particles absorb more impact energy, reducing fragmentation during low speed collisions. Porosity also influences light scattering, affecting albedo measurements. Observations suggest a wide range of porosity levels across the rings, with denser regions tending to contain more compacted particles, while diffuse areas harbor more loosely bound aggregates. Composition variation exists both between rings and within individual particles. While water ice dominates, small inclusions of rock, silicates, and organic compounds are found throughout. These variations create subtle spectral differences detectable in reflected light. Spectroscopy across visible and infrared wavelengths allows scientists to determine the relative abundance of ice versus impurities and to detect minor compositional variations between dense bands and less dense regions. Some areas show a higher fraction of rocky material, often corresponding with regions of lower albedo or where meteoroid bombardment has been more intense. Microscopic structures on particle surfaces reveal the history of collisions and erosion. Craters, grooves, and irregularities indicate repeated impacts and particle fragmentation. Fine scale roughness influences how sunlight is scattered, contributing to brightness variations seen in imaging. Surface texture affects thermal behavior as well. Rough surfaces absorb and emit heat differently than smooth ice, contributing to local variations in temperature and sublimation rates. The reflectivity of ring particles depends on both intrinsic material and surface condition. Clean ice surfaces are highly reflective, while embedded dust or irradiation darkened layers reduce albedo. Reflectivity also varies with viewing angle and wavelength, revealing details about surface roughness and particle size distribution. Observations across multiple angles and spectral bands provide a comprehensive understanding of particle surfaces, indicating the degree of freshness or weathering over time. Temperature variation across the rings is not uniform. Dense regions and can retain heat differently than sparse zones. Particles in close packed areas transfer heat more effectively through mutual shadowing and radiation, while isolated particles experience faster cooling in Saturn's shadow. Seasonal changes in solar illumination also affect temperature distributions, with some regions warming more during periods of direct sunlight and cooling during long shadow passages. These thermal cycles contribute to slow changes in particle surface structure, sublimation, and ice redistribution. Impacts play a continuous role in shaping particle surfaces. Micrometeorites produce small scale cratering, eject dust, and occasionally expose fresher ice beneath weathered layers. Over time, repeated impacts help maintain a dynamic surface environment where particles are constantly modified but rarely destroyed entirely. Fine ejecta from impacts can spread through the rings, supplying material to adjacent regions and contributing to the redistribution of ice and dust. Porosity also influences particle interactions. Aggregates with higher porosity absorb collisions more gently, allowing temporary clumps to form without significant fragmentation. Lower porosity particles are more prone to shattering upon impact, creating additional small debris. These differences affect local density, particle size, distribution, and energy dissipation during collisions, contributing to the diversity of structures observed in both dense and diffuse rings. Spectral analysis provides insight into particle composition and surface condition. Observations in visible, near infrared, and ultraviolet wavelengths reveal differences in ice purity, the presence of silicate inclusions, and effects of surface weathering. By comparing spectra from various rings, Scientists can identify variations in particle composition across the system, detect subtle gradients in ice purity, and measure the relative abundance of rocky or dusty material. These measurements provide direct evidence of both initial formation conditions and ongoing modification processes. Fine scale surface features influence light scattering and observed brightness. Craters, ridges, and irregularities redirect sunlight, creating variations in intensity and contrast. Dense clumps of particles amplify these effects, while sparse regions display smoother, more uniform brightness. By analyzing light scattering patterns, scientists can infer particle shapes, surface roughness, and local density. These observations contribute to understanding microphysical processes, including aggregation, fragmentation, and collision dynamics. Thermal behavior is linked to both material composition and particle structure. Ice rich, low porosity particles retain heat differently than porous aggregates with mixed compositions. Seasonal variations alter illumination angles, producing temperature gradients that affect sublimation rates and surface modification. Temperature differences also influence local gas release from ice, contributing to redistribution of particles and fine dust across the rings. Micrometeorite impacts contribute to compositional mixing. When a meteoroid strikes, it may deposit rocky material or redistribute existing ice. Continuous bombardment leads to gradual homogenization of surfaces while simultaneously producing small scale heterogeneity. These processes explain why particles in the same ring can have slightly different albedos, surface textures, and spectral properties despite being in close proximity. The porosity and aggregation of particles influence their mechanical behavior. Clumps of loosely bound grains can absorb impacts without breaking apart, while compacted particles are more likely to fragment. This dynamic affects collision outcomes, local density, and formation of temporary structures such as wakes or spirals. Observations indicate that even within dense rings, particle behavior is heterogeneous, reflecting variations in internal structure and surface properties. Surface aging and renewal are ongoing processes. Fresh ice may be exposed through collisions or fragmentation, restoring high reflectivity in some areas. Older surfaces so darken through micrometeorite bombardment and radiation exposure. The balance of these processes contributes to the observed range of albedo across the rings, with brighter regions indicating fresher ice and darker regions showing longer exposure to erosion and dust accumulation. Thermal cycles influence particle cohesion and surface evolution. Heating and cooling cause minor expansion and contraction, affecting porosity and surface texture over long periods. Sublimation removes microscopic layers of ice, while recondensation may redistribute material locally. These effects operate continuously, producing slow, measurable changes in particle surfaces while maintaining the overall structure and appearance of the ring system. High-resolution imaging from Cassini allowed detailed study of particle surfaces. Craters, ridges, and small-scale roughness were measured, providing data on impact rates, particle strength, and surface evolution. Combined with spectral analysis, these measurements revealed variations in ice purity, rock content, and dust accumulation, confirming that microphysical processes are active throughout the ring system and continue to shape particle properties over time. Saturn's rings exist within a complex environment of gas and plasma. While primarily composed of solid ice and rock, the rings are surrounded by a tenuous layer of gases. These include water vapor released from ice particles, molecular oxygen produced through radiation, and trace amounts of other molecules. The density of these gases is extremely low compared to Earth's atmosphere, but they form a persistent exosphere around the rings. This thin layer interacts with charged particles, magnetic fields, and the solar wind, creating a dynamic plasma environment that surrounds and permeates the ring system. The rings are embedded in Saturn's magnetosphere, a large region dominated by the planet's magnetic field. Charged particles within the rings respond to this field, following spiral paths along magnetic lines. Electrons and ions are trapped and accelerated, creating a continuous flow of energetic particles that interact with the ring material. These interactions can influence the motion of dust grains, small ice particles, and even larger clumps, particularly when particles acquire electrical charge through contact, photoionization, or collisions with energetic plasma. The plasma environment near the rings consists of ions and electrons derived from multiple sources. Some come from the rings themselves, released by sputtering and micrometeorite impacts. Others originate from Saturn's moons, such as Enceladus, which emits water vapor that becomes ionized in the magnetosphere. Solar ultraviolet radiation also ionizes neutral particles, producing additional plasma. This charged environment is highly variable, responding to changes in solar activity, Saturn's rotation, and particle density within the rings and surrounding space. The ring ionosphere is a term used to describe the layer of charged particles closely associated with the rings. Electrons and ions are concentrated near dense ring regions, producing weak electrical currents. These currents interact with Saturn's magnetic field, inducing small forces on the ring particles. While the effect on larger ice chunks is minor, fine dust and small aggregates respond more readily. The result is subtle modifications of particle motion, contributing to local variations in density and structure, and in some cases, influencing the formation of faint arcs or spokes observed in certain rings. Magnetospheric interactions affect ring dynamics in multiple ways. Charged particles experience Lorentz forces, which cause them to move along curved paths relative to the magnetic field. This motion can lift small particles slightly above or below the main ring plane, creating small vertical undulations. Particles with higher charge to mass ratios, such as sub-millimeter ice grains, are most susceptible to these forces. Observations of faint, temporary spokes in the B ring indicate that these effects are real, with small particles levitated and redistributed by electromagnetic interactions. The plasma sheet around Saturn consists of a dense layer of ions and electrons concentrated near the equatorial plane, overlapping the ring system. The plasma sheet moves with the planet's rotation, producing flows that interact with ring particles. Collisions between plasma particles and ice surfaces lead to sputtering, gradually eroding surfaces and releasing additional neutral molecules. This continuous exchange of material contributes to the overall plasma content and maintains the tenuous ring atmosphere. The density and energy of the plasma sheet vary with Saturn's magnetic activity and seasonal conditions, producing dynamic changes over time. Energetic particle populations in the magnetosphere contribute to ionization and radiation effects. High-energy electrons and ions collide with ring particles, creating secondary electrons, sputtering ice, and altering surface chemistry. These interactions are particularly important in dense rings where the flux of energetic particles is higher due to local trapping and focusing by magnetic field lines. The energetic environment modifies both the physical and chemical properties of ring particles, influencing reflectivity, albedo, and minor surface composition over long periods. The combination of ring atmosphere, plasma, and magnetospheric interactions produces complex structures within the ring system. Electric charges on particles can lead to mutual repulsion or attraction, influencing aggregation and collision outcomes. In regions with high plasma density, particles may cluster differently than in low-density areas. Observed spokes, arcs, and faint wisps illustrate how charged environments and magnetic interactions shape temporary features without altering the overall ring architecture. These phenomena provide a direct view of ongoing electromagnetic processes operating in the system. Solar radiation also contributes to ionization. Ultraviolet, Light from the sun can remove electrons from neutral particles, creating ions that join the plasma population. This photoionization occurs continuously, especially on sunlit portions of the rings, producing local variations in charge and enhancing interactions with the magnetic field. Day-night cycles across the rings, along with seasonal changes in solar illumination, produce fluctuating ionization rates, affecting particle dynamics and the visibility of plasma-driven features. Saturn's magnetic field exerts control over ring plasma on large scales. The field lines are nearly aligned with the planet's rotation axis, guiding charged particles in helical paths. Particles move in complex trajectories, with motion determined by their charge, mass, and local plasma density. Smaller particles, due to their lower mass, experience greater deviation from simple orbital paths, while larger particles remain largely governed by gravitational forces. This interplay creates a layered environment with plasma-dominated motion influencing small-scale ring structures and gravity dominating the bulk distribution of ice and rock. Magnetospheric currents also generate subtle forces within the ring system. Electric fields arise from differences in plasma density and particle motion relative to the magnetic field. These fields can accelerate small charged particles, creating radial or vertical drift. Over time, such forces contribute to the redistribution of fine particles, maintaining a dynamic equilibrium between electromagnetic effects, gravitational confinement, and collisional interactions. This equilibrium ensures that the rings retain overall coherence while allowing small-scale changes to occur continuously. Observations from Cassini confirmed the presence of plasma and energetic particle populations within the ring environment. Instruments measured ion densities, electron flux, and energy spectra, providing detailed maps of the plasma sheet and ring ionosphere. Measurements indicated that particle energies ranged from low-energy thermal ions to high-energy electrons capable of sputtering ice surfaces. These data have been critical for understanding the balance between particle loss, surface modification, and the maintenance of the tenuous ring atmosphere. Interactions between the plasma environment and ring particles influence the longevity and evolution of the rings. Sputtering removes ice, creating a slow erosion process, while the release of neutral molecules replenishes the ring atmosphere. Charged particle motion can temporarily lift or redistribute fine material, affecting local density and the formation of small-scale features. Over time, these processes contribute to the overall evolution of ring particle surfaces, complementing erosion and replenishment mechanisms already present from collisions and meteoroid impacts. Local variations in plasma density correlate with ring structure. Dense regions with higher particle concentration produce localized enhancements in ion and electron densities. Sparse regions allow plasma to flow more freely, creating differences in electric currents and magnetic interactions. These variations contribute to observable features such as spokes, temporary clumps, and small radial distortions. High-resolution imaging and in situ measurements confirm that plasma effects are most pronounced in regions with fine particles and intermediate optical depth. Plasma-induced electric charges can alter collision outcomes. When two particles carrying similar charges approach, electrostatic repulsion can prevent contact or reduce collision energy. Oppositely charged particles may attract, forming temporary aggregates. These electrostatic effects operate primarily on sub-millimeter to millimeter-sized grains, influencing the formation of small clumps and wakes. In combination with gravitational forces, these interactions create a rich, dynamic environment where physical and electromagnetic effects are intertwined. The ring ionosphere varies with distance from Saturn. Inner dense rings have higher ion densities due to closer proximity to the planet and stronger magnetic influence, while outer rings contain more diffuse plasma populations. Seasonal effects, including solar exposure and Saturn's axial tilt, produce temporal variations in ionization and charge distribution. These factors create dynamic changes on daily, monthly, and yearly timescales, demonstrating that the electromagnetic environment of the rings is both spatially and temporally complex. Interactions with Saturn's magnetosphere also influence the movement of dust. Fine ice particles can be accelerated along magnetic field lines, producing subtle vertical displacement above and below the main ring plane. Such displacements are often transient, with particles settling back into the plane over time, but they contribute to the three-dimensional structure of the rings. Magnetic levitation is particularly noticeable in the formation of spokes in the B ring, appearing as short-lived features composed of micron-sized ice grains lifted above the ring surface. Plasma flows interact with embedded moons and small moonlets as well. Charged particles near these bodies can enhance local currents, producing minor electric fields that modify particle motion. The combined effect of moons, charged particles, and magnetic field lines results in small scale patterns, including arcs, wakes, and temporary distortions. Observations show that these phenomena are continuously forming and dissipating, emphasizing the dynamic nature of the ring plasma environment. Energetic particles contribute to surface sputtering, slowly removing material from ice grains. This process releases water vapor and minor compounds into the ring atmosphere, maintaining the tenuous gaseous envelope. The interaction between erosion, plasma production, and electromagnetic forces forms a feedback loop that sustains both the ring, material, and the surrounding ionized environment. Over long time scales, this continuous exchange influences particle composition, reflectivity, and structural features within the rings. Even regions of low optical depth are affected by plasma. The faint E, G, and D rings experience ionization, electrical charging, and particle redistribution, demonstrating that magnetospheric processes operate throughout the system, regardless of particle density. Fine grains are especially responsive to these effects, and the combined influence of Saturn's magnetic field and plasma flows shapes the structure of even the most diffuse rings. The plasma environment of Saturn's rings is therefore a key factor in their ongoing evolution. It interacts with particle surfaces, modifies collision dynamics, contributes to erosion and material redistribution, and produces temporary features such as spokes and arcs. These interactions complement gravitational forces, moon resonances, and collisional processes, forming an integrated system in which electromagnetic and physical effects together shape the observed structure, density, and small-scale variability of the rings. Observations confirm that ring plasma interactions operate on multiple scales, affecting fine particles, clumps, and local density patterns. The combination of ionization, charged particle motion, magnetic forces, and sputtering establishes a dynamic environment that contributes to the appearance and evolution of the ring system over both short and long timescales. The study of Saturn's rings has relied on both Earth-based telescopes and spacecraft missions. Early telescopic observations allowed astronomers to identify the broad structure of the rings, their divisions, and variations in brightness. Ground-based imaging provided the first evidence of gaps and broad patterns, such as the Cassini division separating the A and B rings. These observations, although limited by distance and atmospheric distortion, laid the foundation for understanding the rings as a complex system rather than a single uniform band of material. Space missions significantly enhanced knowledge of ring structure and composition. The Pioneer spacecraft in the 1970s offered initial close-range observations, confirming ring particle density estimates and providing coarse images. Voyager 1 and Voyager 2, launched in the late 1970s, produced high-resolution photographs and collected spectroscopic data. Voyager imaging revealed intricate structures, including wave patterns, narrow ringlets, and small-scale clumping. Observations highlighted the role of resonances with moons and provided precise measurements of ring thickness and particle distribution. Cassini, launched in 1997, transformed understanding of the ring system. Arriving at Saturn in 2004, Cassini carried instruments capable of imaging, spectroscopic analysis, radar probing, and plasma measurement. The spacecraft captured detailed images of the rings, resolving individual ringlets and fine structures within the A, B, and C rings. Cassini's cameras documented spiral density waves, self gravity wakes, and transient features such as spokes, revealing the dynamic and evolving nature of the ring system. Spectroscopy has been critical for analyzing ring composition. By measuring reflected light across multiple wavelengths, scientists can determine the relative abundance of water, ice, rock, and inorganic compounds. Infrared spectroscopy is particularly useful for detecting ice purity and thermal properties, while ultraviolet observations reveal surface weathering and space radiation effects. Spectral data confirm that the rings contain mostly water ice with variations in purity and composition across different regions, indicating ongoing processes of erosion, replenishment, and contamination by meteoroid dust. Radar studies contribute additional insight into particle size and density. Radio waves, transmitted from spacecraft or Earth, reflect differently depending on surface properties and aggregate size. Radar backscatter measurements indicate the presence of both small, fine particles and larger ice chunks, allowing scientists to model size distributions and local density. Dense regions, such as the B ring, exhibit strong radar reflection, while diffuse rings reflect less, consistent with lower particle concentration and smaller average size. Infrared imaging has been used to map thermal properties and seasonal temperature variations. By observing emitted heat from particles, scientists can determine local temperature differences and infer material composition, porosity, and particle size. Variations in thermal emission reveal patterns not immediately visible in visible light, such as differences between tightly packed ringlets and sparse regions. Infrared data also help identify vertical warping and subtle tilts in the ring plane caused by gravitational interactions and electromagnetic effects. Cassini's close passes allowed for unprecedented observation of transient phenomena. Short-lived spokes, arcs, and local clumping were documented in high temporal resolution, providing insight into processes driven by plasma interactions, electromagnetic forces, and particle collisions. The ability to observe these features over time demonstrated that the ring system is dynamic, with small-scale changes occurring continuously even as large-scale structure remains stable. These observations confirm theoretical predictions about particle charging, levitation, and motion under Saturn's magnetic influence. Imaging of spiral density waves revealed the effects of orbital resonances. As moons exert gravitational pull at specific orbital periods, waves propagate through the rings, creating repeating bright and dark bands. High-resolution images from Cassini captured these patterns in remarkable detail, showing variations in wavelength, amplitude, and radial extent. Such observations allowed scientists to model the interactions between moons and ring particles, linking wave properties to the mass and position of perturbing bodies. Transient clumps and self-gravity wakes were observed within the dense rings. Localized concentrations of particles form temporary structures due to mutual gravity, collisional dynamics, and collective motion. These features are short-lived but consistently appear, illustrating how even in a seemingly stable system, microscale processes constantly redistribute material. Imaging over multiple orbits confirmed the cyclic nature of these phenomena, emphasizing the importance of continuous monitoring to understand ring dynamics. Ultraviolet imaging provided additional data on surface composition and particle weathering. High-energy solar photons alter ice chemistry and produce charged particles, influencing albedo and reflectivity. Ultraviolet measurements reveal differences between fresh ice surfaces and regions affected by micrometeorite impacts or radiation, helping to map variations in ice purity and dust accumulation. These observations complement visible and infrared imaging, offering a more complete picture of particle properties and ring evolution. Multi-wavelength observation allows cross-verification of features. Imaging in visible light identifies structure and density contrasts. Infrared maps thermal behavior, ultraviolet reveals surface changes, and radar provides particle size and density. By combining these techniques, scientists can understand both the composition and physical behavior of ring particles. This integrated approach has been critical in identifying subtle features, confirming models of wave propagation, and assessing the influence of moons and plasma on ring structure. Cassini's prolonged presence around Saturn enabled repeated observation under varying conditions. Seasonal changes, solar illumination, and Saturnian rotation were monitored, showing how light angle and solar exposure influence particle temperature, reflectivity, and feature visibility. Observations over months and years documented long term trends as well as short lived events, allowing scientists to separate transient phenomena from stable structures. This temporal dimension is essential for understanding the dynamic processes that govern the ring system. Radio science experiments from Cassini provided measurements of ring mass and density. By sending radio signals through the rings and observing the attenuation and scattering, scientists could infer particle concentration and total mass of specific ring segments. These experiments confirmed that the B ring holds most of the system's mass, while outer and diffuse rings like the E and G rings contain comparatively little material. Accurate mass measurements inform models of ring evolution, formation theories, and particle redistribution over time. Observations of ring edges, gaps, and divisions have benefited from imaging and occultation studies. Stellar occultations, in which a star passes behind the rings, allow precise measurement of optical depth and particle distribution. These techniques revealed sharp ring boundaries, narrow ringlets, and detailed structure within gaps, such as the Cassini division and Encke gap. Understanding these features clarifies the influence of gravitational resonances, moon interactions, and local particle dynamics. Ground-based telescopes remain valuable for complementary observations. While resolution is limited, telescopes equipped with adaptive optics and spectroscopic instruments can track large-scale ring patterns, seasonal changes, and long-term brightness variations. Earth-based monitoring continues to detect phenomena such as spoke formation, diffuse ring behavior, and occasional brightening events, providing context for spacecraft data and extending observation time beyond mission duration. High-resolution cameras onboard Cassini documented variations within individual ringlets. Small-scale clumping, variations in particle size, and radial density changes were measured with unprecedented precision. Time-lapse imaging allowed tracking of these features as they moved with orbital motion, revealing differential rotation, wave propagation, and local density fluctuations. Such data enhance understanding of how microscopic interactions scale up to influence visible ring patterns. The combination of spacecraft and Earth-based observations enabled comprehensive mapping of the ring system. Detailed atlases of ring structure, particle distribution, and dynamic features were created. Data integration from imaging, spectroscopy, radar, and radio science produced a multi-layered understanding of the rings, showing how density waves, self-gravity wakes, plasma interactions, and moon resonances collectively shape the system. Spectroscopic analysis of reflected and emitted light allowed determination of particle composition across different rings. Variations in ice purity, dust content, and trace organics were mapped, revealing how processes like erosion, micrometeorite deposition, and plasma interaction produce regional differences. These measurements also helped evaluate hypotheses of ring origin and age, linking composition to possible formation mechanisms and subsequent evolution. Saturn's rings are not fixed in place, but gradually change over time. Particles move in orbits that interact with each other and with Saturn's gravity. Collisions between particles, even gentle ones, slowly redistribute material. Small impacts break particles into smaller pieces or combine them into temporary clumps. Over long periods, these interactions cause ring spreading, as some particles drift outward while others move inward toward the planet. The process is gradual but continuous, reshaping the structure of the rings over millions of years. Ring spreading occurs because particles in slightly different orbits move at different speeds. Inner particles orbit faster, and outer particles move more slowly. As they collide, energy is exchanged, which changes their orbits slightly. Over time, this results in the gradual widening of dense ring bands and a slow flow of material toward both the planet and the outer ring edges. Spreading is influenced by ring density, particle size, and the presence of moons, which can either stabilize certain regions or enhance redistribution through resonances. Infall into Saturn is another slow process affecting the rings. Particles gradually lose energy due to collisions, plasma drag, and electromagnetic interactions. Charged particles interact with Saturn's magnetic field, sometimes spiraling inward. Micrometeoroid bombardment erodes ice, and sputtering from plasma removes material from particle surfaces. These combined effects cause a small but continuous loss of ring material as it eventually enters Saturn's upper atmosphere, where it becomes part of the planet itself. Collisions among ring particles drive evolution in both dense and diffuse regions. Frequent low velocity impacts cause gradual rounding of particle edges, reducing surface irregularities and maintaining compact clumps. Occasional higher speed collisions fragment larger chunks, creating fine particles that spread through nearby regions. This constant turnover balances growth and erosion, shaping the observed particle size distribution and influencing local optical depth and reflectivity. Spreading and collisions also interact with resonances from Saturn's moons. Orbital resonances can focus particle movement, creating gaps, waves, or localized clumps. Over long timescales, these resonant effects guide particle redistribution and maintain certain structures, even as the overall system slowly evolves. Shepherd moons, in particular, confine particles at the edges of rings, slowing loss in those areas and preserving sharp boundaries. These gravitational interactions contribute to the long-term stability and organization of the ring system despite ongoing particle movement. Models of ring lifetime suggest that the rings are relatively young on a cosmic scale. Estimates based on mass, erosion rates, and material loss indicate lifetimes of tens to hundreds of millions of years. The B ring, with higher particle density, may last longer than outer or more diffuse rings, which experience faster erosion and spreading. Factors such as micrometeoroid flux, plasma interactions, and collisions all influence the rate at which material is lost, providing a measure for expected ring longevity. Ring dissipation could occur gradually if current processes continue without replenishment. Collisions and sputtering slowly reduce particle size, producing fine dust that is eventually removed by electromagnetic forces or falls into Saturn. Spreading reduces density in the central rings, while material moves outward to the outer limits or inward toward the planet. Over time, these processes could lead to thinning and fading of visible rings, eventually leaving only residual, sparse structures. Renewal scenarios are also possible. Collisions or fragmentation of small moons or larger ring particles can supply fresh material to the rings, replenishing lost ice and dust. Impacts from comets or minor bodies may contribute new ice and rock, maintaining particle population and reflectivity. In some cases, tidal disruption of an incoming object could provide a significant pulse of material, temporarily enhancing ring density and structure. Such events may have occurred in the past, explaining bright regions or newly formed clumps observed in dense rings. Particle redistribution may also create temporary bright or dense features. Collisions and spreading can concentrate material in certain regions, forming clumps or wakes that appear brighter in reflected light. These features are short-lived on the scale of years to decades, but demonstrate how the system can reorganize itself, while overall material gradually decreases. Observations of these processes provide insight into the balance between erosion, redistribution, and potential renewal events. Over long timescales, Saturn's rings will continue to evolve under the combined influence of collisions, spreading gravitational resonances, and plasma interactions. Dense regions like the B ring may persist longest, while more diffuse outer rings may fade first. Micrometeoroid bombardment, plasma sputtering, and gradual infall will steadily remove material, altering the appearance, optical depth, and composition of the rings. These processes highlight the transient nature of the system in a cosmic context. The balance between erosion and potential renewal events determines ring evolution. In the absence of significant new material, particles will continue to fragment, redistribute, and slowly fall into Saturn. Occasional replenishment events, however, could temporarily reverse decline, adding ice or rock to maintain brightness and density. Models incorporating observed particle sizes, mass estimates, and plasma interactions suggest that the rings are in a dynamic equilibrium, slowly aging but still retaining recognizable structure. Long term predictions indicate that visible rings may not survive indefinitely. Current models project a future in which some regions dissipate entirely, while others maintain structure for longer periods. Denser rings are likely to endure tens to hundreds of millions of years longer, while faint outer rings may become undetectable first. Over geological timescales, Saturn's rings may transition from their current bright and structured state to a sparser, more diffuse system, blending with the planet's broader environment. Collisional processes also affect particle size distribution. Over millions of years, larger chunks gradually fragment into smaller pieces, increasing fine dust populations. Fine dust interacts more strongly with electromagnetic forces, plasma flows, and solar radiation, accelerating redistribution and infall. Dense regions maintain larger aggregates, longer due to mutual gravitational attraction and shielding from small particles, but erosion continues to operate at all scales. This ongoing cycle gradually reshapes ring structure and appearance over time. Electromagnetic and plasma interactions contribute to slow ring evolution. Charged particles experience forces that can remove fine ice grains or alter their orbits, subtly affecting density patterns. Seasonal changes in solar illumination modify ionization and plasma density, producing small variations in particle dynamics. These effects operate continuously, combining with collisional and spreading processes to determine the long-term evolution of the ring system. Observations of ring microstructure suggest that dynamic processes have been ongoing for millions of years. Spiral density waves, self-gravity wakes, and temporary clumps indicate persistent redistribution and evolution of material. Even stable-looking regions show evidence of continuous modification at microscopic and local scales. This ongoing activity ensures that the rings remain a changing system, with both predictable and stochastic processes operating simultaneously. Saturn's rings are not only remarkable for their beauty and complexity, but also for the scientific insights they provide. Studying the rings helps researchers understand how planetary ring systems function and evolve. Observations reveal patterns of particle motion, density waves, and interactions with moons and magnetic fields. These data provide a natural laboratory for testing physical models of orbital dynamics, collisions, and electromagnetic effects. The processes observed in Saturn's rings illustrate fundamental principles that apply to other ring systems and debris structures throughout the solar system. Comparisons with the rings of other giant planets highlight both similarities and differences. Jupiter's faint rings consist mostly of small dust particles maintained by micrometeoroid impacts on its moons. Uranus has narrow dark rings with sharp edges, while Neptune's rings are incomplete and contain arcs. Saturn's rings are distinct for their size, brightness, and particle density, but studying all planetary rings together allows scientists to explore how mass, gravity, and the presence of moons influence ring structure. This comparative approach provides a broader perspective on the mechanisms that govern ring formation, maintenance, and evolution. The rings also inform models of planetary formation. Rings represent collections of material that may resemble the debris present in early planetary disks. The distribution of particle sizes, collisions, and aggregation processes in Saturn's rings offers insight into how dust and ice coalesced to form larger bodies in the young solar system. Observing waves, clumps, and gaps helps scientists understand how orbital resonances and gravitational interactions shape disk structures, providing analogs for protoplanetary environments around young stars. Studying the rings also contributes to understanding debris dynamics. Particle collisions, fragmentation, and redistribution observed in Saturn's rings illustrate how debris fields evolve over time. Small scale processes such as aggregation, erosion, and plasma interactions demonstrate the balance between forces that maintain coherent structures and those that disperse material. These insights are applicable to a range of phenomena, including asteroid belts, cometary debris, and circumstellar disks, where similar processes occur on different scales. Ongoing research focuses on open questions about the origin, age, and future of the rings. Determining whether the rings formed alongside Saturn or are the result of more recent events remains a key question. Measurements of mass and composition and particle size distribution continue to refine models of ring formation and evolution. Investigations into the role of micrometeoroid impacts, plasma interactions, and gravitational resonances enhance understanding of how ring features are maintained and modified over time. The fine scale structure of the rings remains an area of active study. Spiral density waves, self gravity wakes, and transient spokes are still being analyzed to understand their formation and persistence. Observing these features provides clues to the interplay between gravity, collisions, and electromagnetic forces. Detailed models can predict how these structures evolve, offering insight into the mechanisms that maintain stability in otherwise dynamic and changing environments. Saturn's rings also serve as a reference for planetary ring science beyond the solar system. Observations of exoplanetary systems suggest that rings and debris disks are common, but resolving details at such distances is challenging. By understanding Saturn's rings, scientists can interpret indirect observations of distant systems and infer properties such as particle size distribution, disk thickness, and dynamical interactions. Saturn provides a benchmark for understanding disk evolution and the physical processes that shape planetary environments elsewhere. The study of ring composition continues to be important. Variations in ice purity, contamination by dust, and trace organics reveal the processes that influence particle surfaces and ring evolution. Spectroscopic analysis informs models of material origin, age, and surface modification. Combining compositional data with structural observations enables a more complete understanding of how rings form, persist, and interact with their surrounding environment. Long-term monitoring of Saturn's rings offers insight into seasonal and temporal changes. The planet's tilt, orbital position, and solar illumination affect particle temperatures, plasma interactions, and visibility of certain features. Observing these variations over time contributes to understanding the dynamic behavior of the ring system and helps calibrate models that predict future evolution. Longitudinal studies provide a temporal context for phenomena that appear transient but are part of ongoing cyclical processes. The interaction between rings and Saturn's moons remains a key area of study. Shepherd moons, embedded moonlets, and larger satellites all influence ring structure through gravitational forces. Orbital resonances create waves, gaps, and edge confinement, demonstrating the interplay between small bodies and larger planetary systems. Understanding these interactions provides insight into how moons and rings co evolve and how gravitational relationships influence the stability and longevity of planetary systems. Finally, Saturn's rings continue to inspire exploration and observation. Space missions such as Voyager and Cassini have transformed knowledge, but questions remain. Future missions may provide higher resolution imaging, in situ sampling, or extended temporal coverage. Each observation enhances understanding of ring dynamics, composition, and evolution, contributing to broader planetary science. The rings serve as a natural laboratory for studying processes that operate across scales, from microscopic particle interactions to large scale orbital mechanics, offering a continuous source of scientific discovery. The study of Saturn's rings demonstrates the value of integrated observation and modeling. By combining imaging, spectroscopy, radar, radio, and plasma measurements, scientists can interpret structure, composition, dynamics, and evolution with greater accuracy. Understanding how the rings operate informs broader concepts in planetary formation, debris dynamics, and the evolution of complex systems. Each insight contributes to a more complete picture of planetary ring systems and their role in shaping solar system architecture. Research on Saturn's rings also informs the interpretation of newly discovered ring systems beyond our solar system. The principles learned from particle dynamics, collisional processes, and orbital resonances provide a framework to infer properties from limited or indirect observations. This comparative approach allows scientists to apply lessons from Saturn to other planets, helping to place the solar system in a broader astronomical context. Continuing study of the rings focuses on unanswered questions about formation mechanisms and material sources. Determining whether the rings are primordial, remnants of moon disruption, or replenished by ongoing processes is central to understanding their history. Particle redistribution, collisional evolution, and plasma effects remain under investigation, contributing to an ongoing picture of ring dynamics. Each new dataset refines existing models and helps predict how the rings will evolve in the future. In summary, Saturn's rings are both a subject of detailed study and a source of broader scientific insight. They reveal the interplay of gravity, collisions, electromagnetic forces, and material composition. By comparing them to other planetary rings, researchers gain perspective on the diversity of ring systems. Through continued observation and analysis, Saturn's rings inform understanding of planetary formation, debris evolution, and the mechanisms that maintain or alter complex systems. They remain a key focus for planetary science, offering ongoing opportunities to learn about both local and distant environments in the solar system.